But what if Google's Willow quantum chip represented something far more profound than just an advance in computing speed? In December 2024, the company announced that its quantum processor had completed a test in just a few minutes that, according to estimates, would take an absurdly longer time, longer than the age of the universe itself, to reproduce using a conventional supercomputer. The achievement drew attention not only for its speed but for the way quantum computing works. Unlike traditional computers, which process information using bits limited to 0 or 1, quantum computers use qubits, capable of existing in multiple states simultaneously through quantum superposition. But before we continue, don't forget to like and subscribe to our channel. When these qubits become entangled, the system begins to explore a vast number of possibilities at the same time, creating a computational space that grows exponentially. It is precisely this characteristic that has led some physicists to consider extremely unusual interpretations of quantum mechanics. One of the most intriguing is the so-called many-worlds interpretation, which suggests that every quantum possibility can exist in different branches of reality. Although this idea remains highly debated, it fuels speculation about how quantum systems manage to tackle problems that seem impossible for classical computers. Willow has 105 qubits that are carefully isolated and cooled to temperatures near absolute zero to minimize external interference. Despite its unassuming appearance, it represents one of the most advanced experiments ever conducted in quantum computing. We still don't know exactly how far this technology can go. But one thing is already clear: quantum computing is opening up a new scientific frontier. Whether by exploring deep properties of physics or creating machines capable of solving problems currently considered impossible, Willow marks an important step toward a much broader understanding of reality itself. That is where Willow becomes unsettling. If a tiny chip can process a space of possibilities larger than any classical machine could realistically keep up with, then the natural question is not just how fast it is, but what physical reality itself is doing while the calculation takes place. Because the answer may not be entirely contained within a single, shared universe. The idea of parallel universes in quantum mechanics stems from the many worlds interpretation, originally developed by Hugh Everett in the 20th century and later taken seriously by leading thinkers in quantum computing, including David Deutsch. In this view, the wave function is not merely a mathematical tool for predicting probabilities, but a real description of reality itself. The most intriguing aspect of quantum computing is not just its speed, but the way it seems to challenge our understanding of reality. Unlike traditional computers, which analyze one possibility at a time, quantum computers explore countless possibilities simultaneously through superposition and quantum entanglement. This characteristic has led some physicists to revisit one of the most controversial interpretations of quantum mechanics: the many-worlds interpretation. According to this idea, when a quantum event occurs, reality does not choose just one outcome. Instead, all possibilities continue to exist in different branches of the universe. Although this hypothesis remains highly debated, it arises directly from quantum equations and offers a way to explain why quantum systems can process enormous amounts of information. Instead of relying on a single logical path, they utilize a phenomenon called quantum interference, in which different possibilities combine, cancel each other out, or reinforce one another until the most probable outcome emerges. This is exactly what makes processors like Willow so fascinating. With its 105 qubits operating near absolute zero, the system can produce computational patterns that would be practically impossible for classical computers to reproduce within any reasonable time frame. A simple way to imagine this difference is to think of a maze. A traditional computer tests paths one at a time. A quantum computer, on the other hand, explores multiple routes simultaneously, eliminating useless paths and highlighting those that lead to the solution. This does not mean that Willow is literally accessing parallel universes. That remains just one of the possible interpretations. But the performance of these systems is forcing scientists to reconsider fundamental questions about information, probability, and the very nature of reality. Perhaps the greatest discovery of quantum computing is not technological. Perhaps it is philosophical, revealing that the universe may be far stranger than we ever imagined. Despite all the attention generated by Willow, it is important to understand a fundamental distinction. Google's quantum chip has not proven the existence of parallel universes. Physicists continue to debate which interpretation of quantum mechanics correctly describes reality. However, Willow has transformed a discussion once considered purely philosophical into a practical issue of computing. When a quantum computer performs calculations impossible for classical machines, an inevitable question arises. Do these countless possibilities exist only as mathematical abstractions, or do they represent something physically real? The many worlds interpretation suggests that each possibility continues to exist in different branches of reality, allowing quantum interference to produce extremely efficient results. Although this idea remains speculative, it helps illustrate why quantum computing seems so strange. But Willow's most important breakthrough may not be its speed. The real milestone lies in quantum error correction. Qubits are extremely sensitive to their environment, and for decades, the field's greatest challenge has been scaling up systems without drastically increasing errors. Willow demonstrated something unprecedented. As the number of qubits grew, the error rate decreased. This result suggests that fault-tolerant quantum computers may finally be viable. Instead of becoming more unstable as they grow, future machines may be able to preserve their quantum states long enough to solve truly complex problems. Behind this breakthrough lies an even deeper question. To correct errors, the system must preserve extremely delicate quantum entanglements before they collapse into conventional outcomes. In a sense, Willow operates at the frontier between the classical world we know and the hidden quantum structure that underpins reality. For this reason, Willow represents more than just a new processor. It is an important step toward an era in which computing could reveal not only new technologies, but also new insights into the very nature of the universe. Speed is something we already understand. Faster and faster machines have emerged throughout history, from mechanical calculators to modern supercomputers. And each time, humanity has adjusted its expectations. But Willow seems different because it doesn't just accelerate the classical path. It seems to step off it. A classical computer operates by following a single logical chain within a defined physical system. A quantum computer, on the other hand, shapes possibilities before they become final outcomes, allowing superposition, entanglement, and interference to perform work that no conventional sequence of bits could ever mimic. That's why the idea of parallel universes comes into the conversation. Not because scientists claim that Willow has opened a portal, but because a serious interpretation of quantum mechanics suggests that these possibilities may not be mere mathematical shadows. They may be real branches of reality. If this interpretation is correct, then quantum computing isn't just using probability in a clever way. It is utilizing the very structure of the multiverse, where countless branches evolve simultaneously until interference shapes the outcome that finally appears in our world. And this transforms Willow into something far stranger than a simple processor. It becomes a physical entity built from superconducting circuits. Is our universe performing this calculation on its own? Or is every quantum computer silently tapping into a greater reality that we cannot see directly? No one can honestly claim that this mystery has been solved. But after Willow, it has become much harder to ignore the question. So, what did Google's Willow quantum chip actually detect? Not a message from another Earth, not a visible gateway to a parallel timeline, and not proof that we can communicate with alternative versions of ourselves, but something far more subtle, and perhaps even more unsettling. A form of quantum interference so powerful that it forces us to reconsider what it truly means to compute. Willow completed in minutes a test that would be effectively impossible for classical computers to reproduce within any cosmically significant timescale. And while this doesn't prove the many worlds interpretation, it makes one thing clear. Quantum machines aren't just better versions of ordinary computers. They are machines built upon a deeper layer of reality. Inside them, qubits do not behave like normal bits. They exist in superposition, become entangled, and interfere with one another in ways that allow useful answers to emerge from an ocean of possibilities. For some physicists, these possibilities are merely mathematical structures. For some physicists, the countless possibilities explored by a quantum computer are merely mathematical tools. For others, they may represent actual branches of reality, coexisting in a vast quantum multiverse. It is precisely this possibility that makes the story of Willow so fascinating. If the many worlds interpretation is correct, the chip would not be performing calculations solely within a laboratory in California. In theory, it could be exploring possibilities spread across multiple branches of reality, using quantum interference so that different possible outcomes contribute to a single observed result in our universe. This doesn't mean we can visit parallel universes or communicate with them, but it suggests that reality may be much larger and more complex than the single timeline we perceive. Throughout history, humanity has repeatedly expanded its view of the cosmos. First, we believed that Earth was the center of the universe. Then we discovered that we orbit an ordinary star. Later, we realized that the Milky Way was just one among billions of galaxies. Now, quantum mechanics may be pointing to an even deeper expansion, not through space, but through the very possibilities of reality. That is what makes Willow so important. More than a technological breakthrough, it represents a new way of thinking about information, computation, and the fundamental structure of the universe. Its true legacy may not be its processing speed, but the questions it forces us to ask. Perhaps parallel universes exist, perhaps not. But quantum computing is demonstrating that nature operates in ways far stranger than we imagined. Willow may not have opened a door to the multiverse, but it has certainly shown that we are still only beginning to understand the deepest mechanisms of reality.